want to tell you first this morning, in the first half of the morning, the things that I wish somebody had sat me down and explained to me at the beginning of grad school 15 years ago or so, because I had to figure them out myself, and I'm going to try to boil them down into about an hour for you. I want to start with a little amusement. This is something that people, this is an early program that people often write when they start realizing that probabilities in language might have something to do with one another. So here I've generated some text. Let's see, what does this say? Berange, Gi, Arc, Arsif, T, Alamid, Gunful, Zero, Os, the S, Bogen. So how did I do this? Well, I picked a letter to start with. Let's say we start over here with O. And I took out my trusty O die. And I rolled to find out what the next letter would be. Oh, and the next letter was N. OK, so I took out my N die next. And I rolled to find out what the next letter would be, I see, and the next letter is space. And then I took out the space die. So every letter is being chosen dependent on what the previous letter is. Okay. So how do you think I picked the weights for these dice? What letters usually follow O? More likely to be consonants, yeah. So you can't quite see it here because some of the sides are very small, but this is actually like a 27-sided die, so there's 26 letters in space. Well, maybe a few bits of punctuation as well. And the probability of landing on a particular side is proportional to the fraction of letters, the fraction of times, the fraction of O's in a sample of English text that are followed by that letter. So this is the O die. It tends to land on letters that follow O. Okay. So we generate, this is kind of pronounceable because you say consonants and vowels tend to alternate. We can do a little better. So this is what's called a 2-gram or bigram model because it thinks about 2 letters at a time. When it picks a letter, it conditions it on whatever the previous letter was. Okay, so let's go up to 3 grams or trigrams. Okay. So here, I picked 2 letters to start with. Let's start over here. Let's see, so we start with TH, and I decided, well, since it's TH, let's roll the TH die, and we pick the next letter being A. And A is actually quite common following TH. So what follows TH? Well, we've got a lot of the, this, that, these. So it's almost always vowels. The vowels are almost never U. And then following HA, T is pretty common. And following AT, space is pretty common, because add is a good way to end a word. And now this is starting to look a little more like English. So this is called again, a trigram model. And we can do a little better if we go up to 4 grams. Okay, so now this is starting to look, this is rather interesting. Mark it by that and the vocal choosing between created from those not frozen opping class in here any days Ludwig voice art the worst. I mean, we're getting a lot of actual English words in here. We can even go a little bit farther. At this point, you may be able to see what the text was from which I chose the probabilities. Maybe someone would like to guess. Anyone guess? So let's see. The breaks out of oppressor of all which the proletariat goest unto German. These 12s. I'll give you a hint. At one point it generated the word creactionary. Well, so there's a term balanced corpus. So a corpus is a collection of text that you can use to do things like estimate probabilities. A balanced corpus is one where you mix different kinds of text. I want it to be fair and balanced, so I used equal parts of Genesis and the Communist Manifesto. So we get these lovely hybrid words like creactionary. So this is a 5-gram language model. So every letter is being generated depending on the previous 4. And you see that we've got a mixture of these 2 kinds of text. We could also do this instead of doing n grams of letters, where n is 5, we could do n grams of words. So this is word trigrams. Every word is being generated given the previous 2. So we have, let's see. Okay, right. We have up here, the bourgeoisie keeps more and more splitting up into two great lights, the greater light to rule the day. And the interests of the conditions of oppression, new forms of struggle in place of Sechem unto the plain of Mora. So, yes, because of the ground of the same character into one nation with one government. So what happened here? We seem to have switched from one kind of text into another kind of text. And the reason is that we have great plagues because of, that's probably from one text, because of the, could be from either, of the ground. So when you've got something like of the, that's kind of a bridge between the two texts. Right? It could be generated from one text, and then once you've got that context, you might generate your next word from the other text. So we tend to go for a while from Genesis and then switch to the Communist Manifesto, or vice versa. Okay, so why am I doing all this? This is kind of fun. In fact, I first saw this when my freshman roommate in college wrote a program to do this just for fun. Okay. So why might this actually be useful? So let me show you a little text that was generated using a trigram model from a corpus. You might guess that this is a different corpus. What can you tell me about that corpus? Maybe. Well, it's not English. Okay. It's not Japanese either. Maybe somebody can guess actually what language it is. Maybe a little closer. Oh, very close. Yeah, it's actually Xhosa, which is closely related to Zulu. Right. So it's a Bantu language of southern Africa. It's Nelson Mandela's native language, for example. And you can immediately tell that it's not English because if you look at the number of Q's and Z's, they're much too high, for example. The number of spaces is too low. That's another way of saying that the words are long. Right. After Q, what letters are showing up after Q? We have a lot of examples of things like QA, right? It doesn't show up very often in English. The Q die in English is almost always going to land on U. It's going to be very, very heavily weighted toward U. But in Xhosa, that's not true. Now, this text over here is English. Okay? So even though this is a terrible model, right? This is only a trigram model. This doesn't look very much like English. This doesn't look very much like Xhosa. They're still good enough that you could tell the difference from randomly generated text. So it might be that there's enough statistics in text, just looking at these trigrams, to be able to tell what kind of text it's coming from. Here's an example with 4 grams. Okay. And again, you might be able to start to see what the text is if you look at the English. Sorry, I don't know why why the colors are fading in and out here. But this comes from the Universal Declaration of Human Rights, which has been translated into, I think now, upward of 400 languages. It's an inspiring document which aims to tell everybody in the world what their basic human rights are, even if there's only 20 speakers of their language surviving. Okay, so that's a little motivation for using probabilities. As we'll see, you can, and I have people do this at the beginning of my course, if you're given some text, it's not very hard to tell from these statistics of the text which letters follow which ones, what language it's written in. And you can do this given a very short substring of the language, say 10 to 20 characters, with fair accuracy if you're only trying to distinguish among a few languages. If you're trying to distinguish between, say, 2 Bantu languages, then you might need a little more text because those look a little more alike, and you might need to go until you find a word or some pattern of letters which is common in one of those languages and not in the other. Okay. But as you get more and more text, you're just aggregating evidence. So one example of QA, maybe you could tolerate in English, because maybe you're talking about the country of Qatar. But if you see a lot of this, then you pretty quickly, the probabilities pretty quickly tip in favor of some other language. Okay. So let's switch to talking about, I might bring a few transparencies back at the lab this afternoon, but let's switch to talking about probabilities and what to do with them. So the goals of this lecture, first of all, I want you to really understand what this probability notation means. How many people are totally comfortable with this? Okay, a majority, but only about 2/3. So what does this expression mean? How can you sling these things around? Should be very comfortable doing that. And where does its value come from? Okay, so that's the notation. And then I want to talk about probability models, which define this function p. So what do we mean by a probability model? We've been talking about language identification. So how would we actually do that? And then how would we evaluate to find out if the model's any good? I want to start here with a word about statistics. So I think the term statistics is misunderstood because most people who take a statistics course in college are taking a course that tells them how to compute means and medians. Or if they're in the social sciences, they try to find out whether there's enough data whether they had enough subjects in their experiments to find out if their answer was statistically significant. I am going to try here to turn some lights off so the contrast's a little better. Is that better? Yes? Okay. There's a problem that the computers here are on the same circuit as the overhead light. So if you turn the wrong lights off, then the machine dies. Maybe they've fixed that now. But. OK, so I think that these are not the real goals of statistics. The real goal of statistics is to enable statisticians to win a lot of money at the racetrack. So we've seen some data, we've seen the past, and we want to figure out what's likely to be the case in the future. And all this other stuff is sort of incidental to doing that. Okay? So this is a big deal in natural language processing. Why do you want to figure out what to bet on? What are the horses?
Depends on what you're doing.
OK, yeah, so give me an example.
Say you're trying to tag parts of speech.
Mm-hmm.
Do you know the part of speech before you can have a better idea of the next part of speech?
Good. OK, so we'll actually get to that, that particular application after the break. So language is ambiguous, right? It's hugely ambiguous. So as we'll see this afternoon, if you give a computer a sentence with some reasonable grammar of English, it'll find maybe tens of thousands of interpretations of that sentence. Okay? That was a really big problem for natural language processing for a long time. In fact, in the 1950s, 60s, one of the earliest applications of computers was this notion of translating from one language to another, because that would bring about world peace and everything. If we could all understand one another, we could all get along. And it completely fell down on this notion of ambiguity. So you have a word like pen, and you don't know whether it's a pig pen or a pen that you write with. And you need to be able to decide how to understand language in context, figure out how to understand language in context. People worked for a long time on grammar-based methods. And it was only when we started adding statistics to our grammar so that we could figure out, of these many interpretations, which ones are crazy and which ones are reasonable, that the field started to become able to produce results of practical use. OK, so when I was in 6th grade, I acted in a school production of Guys and Dolls. Some of you may know the show. It has a song, which I'd play for you if there were time, where all the gamblers are singing about which horse they'd like to bet on. One of the horses that figures in the song is Paul Revere, and somebody sings there's a guy who says if the weather is clear, he's going to win. So I'm translating this as saying the probability that Paul Revere wins if the weather is clear is 90%. Okay. So what does that really mean? OK, so one possibility is it means that's what we've observed in our corpus. In other words, our text. In this case, a history, all the racing broadsheets for the past 10 years. And we've observed that on times when there's clear weather, Paul Revere's won 90% of the time. Now, there's a little problem here in that the racing season is short, and the horses only run for a couple of years. So we may not actually have enough data to make this estimate. In fact, if you look at the past 10 years, Paul Revere hasn't won in most of them at all, because he was never even born. So we probably don't quite mean that. I think this is maybe a better definition. It's kind of science fiction-y, not so practical. That we're asking if we considered a lot of situations where the weather was clear, then in what percentage would Paul Revere actually win the race? Okay. Here's one that is beloved of philosophers, that this is representing your a strength of your belief in Paul Revere winning, given your current knowledge, namely that the weather is clear. And here's the view that I think is probably the best one to take from the point of view of applied math, natural language processing. So that P is just a function symbol. It's like f. You write f of x. This is P. It has a slightly funny notation inside the parentheses, but it's a function where if you give it something to the left of this bar and something to the right of this bar, we'll give you a number back which is between 0 and 1. Right. So we have one probability model P. We might have another probability model Q. And then we could define both of them and decide which one to trust. So we'll come back to that. So here's the meaning of this vertical bar in probability of win given clear. Is that really what it means is a division symbol, but it's not probability of win divided by probability of clear. It's the fraction of the time that you're in clear that you're also in win. Okay, so here we have the set of all events, and I'll come back to this idea of an event space. This gray ellipse is, this pink ellipse is all the events in which the weather was clear, and we're interested in this overlapping part here, which is 90% of the time when the weather is clear. It's the time when Paul Revere also wins. Just the overlap. Okay. So again, this vertical bar is just syntactic sugar. This comma here, this word clear. So I've written it in English, but what it really means, if you wanted to formalize this, is that for every point in this event space, you can ask a question of it. You have a function, clear. Clear asks of a point in this event space, is the weather clear at that point? So if you map this function, you say, where does it return true, you get exactly this pink ellipse. The weather is clear in this section, and it's not clear over here, cloudy. See, it's dark. And this comma here is denotes conjunction. So this is common in logic that you use comma to mean and. Okay, so this is when it wins and the weather's, when Paul Revere wins and the weather is clear. So picks out exactly the points in this intersection. Okay, so what P is doing is, given some set of events, it's measuring the total probability, like the area inside the ellipse, or inside the intersection of the two ellipses. That's what P does. If you want to know how to do this formally, then take a formal probability course and you'll learn measure theory. But I don't want to do it totally formally, but I do want to tell you a little bit about what the required properties of P. So the probability of the empty set is 0. In other words, something always happens. You always get some event. The total probability of this rectangle, so the probability of the predicate that says yes everywhere, is 1. And everything else is in between. So why is that? That's because when x is a subset of y, probability of x is less than or equal to the probability of y. And so that means that any set, like weather is clear, that set is bigger than the empty set. So it's got probability at least 0. And it's smaller or equal to the set of all events. So its probability is at most 1. Just out of curiosity, is it, why am I, let's see. If we've got a set like weather is clear, which is a non-empty set, is its probability necessarily greater than 0? What do you think? So some people think yes. The answer is actually no for a technical reason. So if I throw my pen at this screen, this is the origin, 0, 0. The chance that I hit exactly the origin is 0. That's a non-empty set of events. There is one event in which I hit that part of the screen, but it has 0 probability. 0 probability doesn't mean impossible. I'll give another example. If you have the interval from 0 to 1 on the real line and you throw a dart at it, what's the probability that you'll hit a rational number? It's 0, because the total area on that, or the total length of that line that's taken up by rational numbers is 0. There's hugely more irrational numbers than rational numbers. So probability 0 doesn't mean impossible. That's why I was careful to write these as subset or equal and less than or equal. So this is just a fine point, and not actually of practical importance for most of NLP, just probably worth mentioning on the side. OK, so this is the final thing to look at. Probability of x plus probability of y is a way to get probability of the union of x and y, provided that x and y are disjoint. Okay, so if you have some set, and you can characterize it as a union of two disjoint sets, so you split it into two pieces, then you can get the total probability of the whole set by adding up the probability of the two pieces. For example, maybe there are two ways to win. You could win on a clear day, or you could win on a cloudy day. And maybe we have totally separate models for winning on a cloudy day and winning on a clear day. So this probability is computed by one formula. That probability is computed by another formula, because when it's cloudy or muddy or something like that, all kinds of factors come into play, which are recognized by the p function there and are not recognized in this situation. So in this situation here, you have to take into account the sun in the horse's eyes and the sun in the other horse's eyes and things like that. OK, so now let's start doing some fun stuff. I want to bet at the racetrack. So one way to bet is, I actually used to live near the racetrack in Baltimore, about a block away. You have a little card that you fill out, and you can say who you expect to be in first place, second place, and third place. It's called win, place, and show. And if you're right about all those, then you win a lot of money, at least if the bookies thought that that was an unlikely turn of events. So how likely is that turn of events? How likely is it for all those three things to happen? As we add more and more names to our ticket, as we get a more and more detailed prediction, what do you think happens to this probability? Goes down, yeah. How come? Sorry? Go ahead.
They race together often?
They don't. Well, we know that they're all in the race. The question is it more likely that Paul Revere wins, or is it more likely that Paul Revere wins and a whole bunch of other things happen? Yeah, that's right. So as you add more things here, to the more conjuncts to the left of the bar, then you're zeroing in here on a smaller and smaller, more and more unlikely part of the event space. Yeah?
Wouldn't it be clearer if we still kept using the intersection sign instead of the comma? That it's getting smaller?
Harder to type. It's harder to type the intersection sign.
But here we use the union sign, and it will be more consistent to use the intersection instead of comma, and also it will be, I think, much clearer to see that that area is getting smaller when you have more sets intersecting, right? I mean, it is pedagogically.
Yeah. There's a tension between being in notation between being useful for somebody who's seeing it for the first time and being convenient to deal with on a daily basis. And naturally, probabilists have used a very small and easy to type symbol for something that they're using constantly. You'll get used to it quickly, I think. OK, so this probability gets smaller and smaller. It may be that if there are only 3 horses in the race, then if Paul Revere wins and Valentine places, you're not decreasing the probability anymore by adding epitaph shows. Because if the first horse is in first place and the second horse is in second place, there's only one place for the third horse epitaph left to go, right, in third place. So it might be that we add some things to the left that don't decrease the probability at all. But at least the probability will never increase. Because you're making a more specific prediction. So what are the chances all these things will happen at once? You sure you can read the purple here? No. Oh, you can't read it at all. OK, then you should tell me this kind of thing. So let's try to do something else with the lights. And it doesn't totally kill the power. Better? Yeah. Yes? Good. OK, so if you take an estimate based on a historical corpus, it'll look like this. So this is the number of times the weather was clear, and this was the number of times the weather was clear and all these other things happened. Okay. So the denominator stays the same as you add more conjuncts up here, But the numerator gets smaller and smaller because there are fewer conditions in which all these things happen. So this probability will start going towards 0. Now let's look at the case where we add conditions to the right. So this is often what I want to do, is I'm going to gather some more information that might help me predict whether Paul Revere is going to win. OK, so if you gather all this information, so you're adding more conjuncts to the right-hand side of the bar, now what happens to the probability? Could go up or down, good. And that's because knowing these facts might either increase or decrease our guess about whether Revere is going to win. Okay. So here the probability is more relevant to the case, more relevant to this particular race. So it's less biased. It's closer to what we care about. So a bias means basically that the way that you're estimating the probability, for example, if you ignored all this stuff, might be systematically wrong. That's a bias. Here, this is the right probability that we're estimating as we add in all the relevant facts. The problem is that it gets harder, even though if we could get this probability, it would be the right probability to get. It's harder and harder to get the probability. So what happens if we take a historical estimate? Now the numerator is getting closer and closer to 0. Because we're interested, as we add more things here, we're specializing the cases that we care about. The denominator also, for the same reason, gets smaller and smaller. So whereas here, this got, on the previous slide, this estimate got closer and closer to, say, 0 out of 50. The denominator stayed at 50. Here, in this case here, the probability is getting closer to So what happens as we add more and more conditions? Suppose we also say it's a full moon. This goes down, that goes down. So the probability gets closer to 0 over 0, which is undefined. So we just don't know. The numbers are too small, right? Suppose this is 1 over 1. Do we think the probability is 100%? Probably not. There was one time when all this stuff happened in the past. And Paul Revere won, 100%? I don't think so. Paul Revere didn't win, 0%? I don't think so. Quite often, this will be 0 over 0, right? This particular conjunction of events has never happened before. So just doing this is not going to help. So this is the fundamental problem. At this point, I have to tell a joke. There was a guy stumbling around in front of a bar. Somebody comes out of the bar and says, sorry, did you lose something? Looks like you're looking for something. He says, yeah, I dropped a $20 bill. Says, well, you've been looking around for a while. Are you sure this is where you dropped it? He says, no, I dropped it down there. Says, so why are you looking here? Says, because the light's better. So this is an example of, deciding to use, deciding to do this is a case of looking for the right thing, but the light's not so good. So what we may want to do is ignore some of these things. That's looking where the light's better. Okay? So it's the wrong probability, but at least we can get a reasonable estimate of it based on historical data. And this is often called backing off. So one way of thinking about it is when we're looking at this, we're staring at a tree. And all of our data is coming from that particular tree. We're not generalizing at all. Here we're backing off and looking at the whole forest. We're looking at a forest of lots more examples. Only the examples that, it's not the particular tree we care about, but we're getting data from other trees as well. And that allows us to get a more reliable estimate. Because we're not just focusing on one example that might or might not, one example from the past that might or might not predict the future. Okay. Good. So let me stop here for questions. Okay, let's race ahead. So how do we know which things to cross off here? Well, we might just try to keep the conditions that we think are have the most influence on whether Paul Revere should win. So we don't really care about the date of the race or who owns the other horses. What we care about is the weather's clear and that this fearsome competition is also in the race. Okay, so let's go back to this other case here where we've got a complicated ticket. So what happens if we do that? Play the same trick. Yeah, unfortunately, the probability goes up if you do that. So we just can't do this. Not only is it, if we cross some things off from the right-hand side, the probability might go up or down, but at least it's the right kind of probability. Here, we're just sort of like assuming that if Paul Revere wins, these other things will happen if we try to use this to estimate this. Okay. So just crossing things off certainly can't be the right answer. The more things you cross off, the higher the probability goes. And so it wasn't a good estimate of the original smaller probability that you wanted. OK, so we can't do that. But we can do something similar. So this is called the chain rule. So this is a way of rewriting exactly the probability that these three horses win. And it's probably easiest to read from bottom to top. So if the weather's clear, what's the chance that Epitaph is in third place? Okay. Suppose that's suppose that's true half the time. Okay. Well, in those half of the times when the weather's clear that Epitaph wins, that Epitaph's in third place. If Epitaph's in third place, what's the probability that also Valentine is in second place? And maybe that's another 10% of the 50%. And then maybe another 30% of the 10% of the 50%. So once we've got the weather being clear and Epitaph in third place and Valentine in second place, what's the probability that Revere then wins? Okay? So we're taking a fraction of a fraction of a fraction. You can think about this as making a sequence of choices. What's the probability that your life is branching? You make a decision to go this way or that way, and you decide to go that way, and it splits further, and the probability divides into pieces. So if you want to convince yourself that this is true, remember that this vertical bar just means division. Okay. So what we're trying to get here is the probability of these four things, Revere, Valentine, Epitaph, and the weather clear, divided by the probability of the weather clear. Okay, these aren't counts, these are just probabilities. Remember, this vertical bar is just syntactic sugar, means the quotient of two probabilities. So we have the quotient of those four things divided by that one thing, and all I've done is factor that into three quotients, and the numerators and denominators cancel, and we clearly get that back. Okay. So why did we bother to do this? Well, once we've moved stuff to the right of the bar, then we can back off. So we can play that game. So now we're estimating the probability of these three horses being in the respective positions by a product of three independent predictions. What's the probability Epitaph will be in third place, that Valentine will be in second place, that Revere will be in first place, and we pretend these are all independent of each other. Is that correct? Are they, in fact? No. How do you know they can't be? Or almost can't be? Sorry?
Can't all be first.
Because they can't all be first, yeah. So once we know that Valentine and Epitaph are in second and third place, that increases Revere's chance of being in first place. So crossing these things off probably actually did reduce the probability from what it would have been if we'd kept them in there. But this is not a totally crazy assumption. In this particular case, we might be able to improve it a bit, but this is sort of a general pattern of how you can estimate lots of things happening at once, is you use the chain rule to divide these off and then decide what's worth ignoring. So maybe in this case, these weren't worth ignoring. Let me give you the terminology. By crossing these off, the assumption that we're making is that whether Revere wins is independent of whether Valentine places and Epitaph shows. Okay. Not quite independent, but conditionally independent. So all we said is if the weather is clear, they're independent of each other. that whether Revere wins is unaffected by these two events, if the weather is clear. Okay. So we might say it's completely different on a muddy day, on a cloudy day. It's completely different. If the weather is not clear, then maybe suddenly their fates are coupled. But they're independent if the weather is clear. So that's why we say conditionally independent. And this conditional independence is an engineering assumption in practice. Okay, so we decide what we're willing to, you can test it against data. If you have enough data to be able to find out whether that assumption is motivated. But in practice, this is something we do when we don't have enough data to get what we really want, is we look where the light's better. And there's a corollary to the joke, which is that the guy says, well, have you found your $20? 60 cents of it. OK, so let's get back to language identification. So here we have a sentence. Horses and Łukasiewicz are on the curriculum. And the only reason I knew how to pronounce that was I was doing language ID on pieces of the sentence. Anybody know who Łukasiewicz is? It's the guy who invented Polish notation, otherwise known as prefix notation. And since this is hard to pronounce, people, actually that L should have a slash across it. People call it Polish notation. And if you've ever had an HP calculator, it uses reverse Polish notation, where you write 3, 4 plus instead of 3 plus 4. So suppose we have to decide, we have to pick a single language for the whole sentence. So what do we think the language is? Okay, well, there was some idea of using n-gram models. So do we think that this is good English? Do we think that English dice would be likely to generate this sentence? Or do we think that Polish dice would be likely to generate this sentence? Maybe instead of dice, I should talk about monkeys typing randomly, right? Except you have English monkeys and Polish monkeys, right? And, or maybe it's not the monkeys. Maybe it's the keyboards they're typing on. So, if you're banging this kind of keyboard, you're likely to get you're likely to get English letters and pairs of English letters, because things that tend to occur together are next to each other. And when you slam your monkey paw on the keyboard, you tend to get English bigrams, whereas the other monkeys were using Polish keyboards. So we can ask, what's the probability of generating that sentence using English monkeys or English dice? And also, what's the probability of doing it using Polish monkeys or Polish dice? And if one of those probabilities is much higher, then it's a good bet that that's the actual language that this came from. Of course, this is hugely unlikely to be generated from either kind of monkey, right? But if you leave the monkeys long enough, eventually they'll type out the works of Shakespeare, both in translation, both in English and in Polish translation. Right? And the question is kind of which they do first. You could actually do this, right? You could say, let's take a random number generator, which simulates these dice. Actually, I didn't really roll dice. I used a random number generator to generate the text we saw before. So let's take a random number generator and generate some text, and we'll just keep doing it until we get this sentence. And we'll have the English program on this computer and the Polish program on that computer, and they'll race. And whoever does it first wins. There's a problem that the universe will probably expire of heat death first. Okay? So, but fortunately, we can use math and do something cheaper, which is instead of actually running the random number generator, we could ask, what's the probability? How often would the random number generator generate exactly this sentence? And that's much faster. So we actually know the sentence. We don't have to generate all the others. We can say, how often would this sentence be generated? And the answer will be, once in a gazillion years. Question?
Yeah, but why? I don't understand why you want to assume things like monkeys or things, but not humans or to machines. Like, what is the idea behind this? To keep things independent? Something like that?
The idea is that we would really like to be able to say, what's the chance that an English-speaking human would type this sentence versus a Polish-speaking human? Okay. Now, the question is, how much engineering effort should we invest in modeling a human? Okay. We could decide to condition on all kinds of things. We know that we could decide to model the human's emotional state and their complete knowledge of language and what they ate for breakfast that morning. But instead, we back off heavily from that. This is exactly the business of looking where the light's better. It's the same kind of back off. We back off heavily and say, you know, even if we have really crude models of the English-speaking human, which looks like a red die, set of red dice, and really crude models of the Polish-speaking human, which look like a set of blue dice, and all they're doing is bigrams or trigrams, those models are still good enough to be able to do a good job of distinguishing English from Polish. And we can come up with if we're modeling the dice, then we don't actually have to take human brains apart. All we have to do is take corpora apart. So we take a corpus of text. It's very easy to estimate how often Q is followed by U. Okay. So we can actually build these models and estimate their parameters and use that to guess whether this is more likely to be English or Polish. Okay. Now, if you wanted to figure out something more complicated, for example, what the person probably meant by that sentence, then this trick wouldn't work. So this trick is only trying to do something very simple, which is based on a character sequence, distinguish which model generated it. But if the model were more complicated, if you were trying to distinguish not an English speaker from a Polish speaker, but an English speaker who meant to say this from an English speaker who meant to say that, then your model has to be dependent on more than just letter frequencies. Okay. And so we'll get to a little closer to that this afternoon. So now our space of events, that big rectangle, is no longer races. It's now character sequences. Okay, so we have the sequence x1 is the first letter in the sentence, x2 is the second letter, x3 is the third. And we'll have this special end of sentence symbol. So once your die comes up with a special end of sentence EOS symbol on top, that means stop. Okay? So that's how we'll manage. So in principle, this sequence is infinite. And we want to be able to generate variable length finite sentences. So this is a reasonable convention for doing that. We'll generate up through the EOS symbol. Other questions? All right. So here we've got two probabilities. We've got the probability of the text in English and the probability of the same text in Polish. And we'll ask which probability is higher. So I'm going to gloss over this point for the moment. It might be that, let's see, you can't tell whether this language, whether this very short text, we've got some 10-letter text, and we can't quite tell whether it's English or, say, Pipil, which has about 20 speakers, certainly fewer than 50. If you had to guess, if you just weren't sure, which one should you bet on? Probably English, because a lot more text is in English. Right, it's a priori more likely. Suppose your model says Pipil is probably a Pipil speaker would be 3 times more likely to generate this text than an English speaker. You might still bet on the English speaker, because where are you going to find a Pipil speaker? You have to travel to South America in the Amazon basin somewhere, I think, and hack your way through lots of underbrush. And probably, even if a Pipil speaker would have been likely to generate this text, you probably didn't have one to start with, so it was probably still generated by an English speaker. So you're generally trading off this probability with the a priori probability that you were generated from P and Q. And if you know Bayes' theorem, then you can see how to put those things together. I don't think have time to go through that this morning. OK, so our question now is, what's the probability that we would have generated this particular sequence of letters from the English model? All right, well, we've already talked about one good model for getting that, right, which is like a trigram model. So let's see how we can get a trigram model. Let's apply the same techniques we looked at before. Okay, so we've got a lot of things on the left-hand side of the bar. In fact, we have nothing on the right-hand side of the bar, unless you want to say on the right-hand side of the bar is English. So what's the probability we would have generated these if we were speaking English? So we could write it like this. The probability that the first letter is H, and then if the first letter is H, that the next letter is O, and then if the first 2 letters are HO, that the next letter is R. So again, we're subdividing the probability space. First into all the sentences that start with H, then into, of the ones that start with H, continue with O, and so forth. So let's see what happens if we estimate these probabilities from a corpus. The corpus I'm going to use here is a balanced corpus, a little better than the one I showed you before. It's called the Brown corpus. It was collected in the 1970s at Brown University by Francis and Kuchera. And we see that of 52,000 sentences, about 1 million words in the Brown corpus from all kinds of different genres of text, news text, fiction, narrative, and so forth. 52,000 sentences, 4,400 started with the letter H. Okay. So if you just take the naive estimate from data, we're going to say that fraction of the time we're going to start with H. Of those 4,470 sentences that start with H, 395 continue with O. Of those that start with HO, 5 continue with R, and so on down. Okay. So you'll notice these estimates up here are probably pretty good because they're based on a lot of data. This one down here, I don't know, do you think it's really impossible in English that HORSE is followed by another S? 0/3 must be impossible, right? We've never seen it before. There are 3 sentences that start with horse in the Brown corpus, but there are no sentences that start with horses. Okay, so what are we going to do? Back off. Look where the light's better. Okay, so if we back off, where every letter, we ignore everything before the previous 2 letters, now these numbers start to go up. Okay. And we see that our probability is a little less than 1 in a billion. So this is like a trigram model, right? For every letter, we're conditioning it on the 2 previous letters. This is saying if of all the sentences in the Brown corpus, and there are 126 of them, where the 3rd letter is R and the 4th letter is S, in what fraction of those, about 1/10, is the 5th letter E? Okay, is this quite a trigram model? Not quite. What's wrong with it? It's biased toward the start of the sentence, right? Which might be good, right? Because that's less biased. After all, our question was, does the sentence start with horses? Right, so it might be good. On the other hand, these numbers are still a little bit low. So how does this, what would a trigram model do differently from this? How, in other words, your point, I think, is that this is paying attention to particular positions. It's only at the start of the sentence, right? Yeah, Adam.
It would be tracking in groups of 3 in sequence.
So this is groups of 3 in sequence. This is 3, 4, 5, and this is 4, 5, 6. But these dice don't know whether they're at position 3 in the sentence or position 5 or position 22, right? So in the trigram model is what's called a stationary model, which means that the probabilities are the same at every time. Okay, as these numbers, so the probability of x15, x13, x14 is the same as x5, x3, x4. Okay? And what we have here doesn't show that. So let's see how we can get there using the kind of manipulations we've seen so far. I'm just going to change the notation a little bit. So what I've done now is said exactly the same thing. Instead of 3, 4, 5, I'm saying I minus 2, I minus 1, I, and also saying I equals 5. Okay, so this is exactly the same. If I is 5 and I minus 2, which is 3, is R, and xi minus 1, x4 is S, what's the probability that xi, x5 will be E? So I haven't changed anything. All these numbers are still the same. The result is still the same. But what can I do now that I've changed the notation this way? I can back off. So I can say, let's ignore the position now. So now this probability model is asking for the probability of that for overall i's, that if xi minus 2 is R and xi minus 1 is S, that the next letter would be E. Okay. And now see how much better estimates we can get of the probabilities. We now have 12,000 examples of RS. And before it was a little less than 10%. Now it's considerably more than 10% of those are being followed by E. So this is just back off. You know, these probabilities could go up or down. Some of them probably went up. Some of them probably went down. But they're more reliable estimates. When we say that, now I can tell you what I mean when we say that these estimates have high variance. What it means is that these estimates are based on the Brown corpus. Now suppose we also had, say, the green corpus, which is the same kind of text, and the yellow corpus. All of these are based on just a small amount of data. So these ratios will probably vary a lot from corpus to corpus. That's what we mean by high variance. It means that we're sort of being enslaved by the particular training data that we got. And in other words, if we trust the training data, we may get an inaccurate estimate. The variance decreases as we get more and more training data. And instead of 3 over 485, these numbers get multiplied by 10 or 100 or something. Then as we start to get more data, we'll zero in on the correct answer. But the Brown corpus is not big enough for us to really trust these numbers. If, on the other hand, we back off, now these numbers are big enough that, that we don't have to be so worried. Okay, and notice that our estimate is now very different. It's gone up by nearly 3 orders of magnitude. Okay? So now this is, instead of a little less than 1 in a billion, it's a little less than 1 in a million. And that's only because our estimates are now more reliable. I believe this answer more than, personally, I believe this answer more than that one. Okay, just because these numbers look too small to me. We could find out by trying some other corpora. For example, we could use the web, that's a really big corpus, find out how likely a sentence is to start with horses. But I would put my money on this one for the moment. Now, there are better ways to build models. You can play some tricks where you interpolate between this model and that model. So where this model has enough data, you trust it, and where it doesn't, then you start to gradually move toward this model. I don't want to go into that this morning because we don't have time, but you should just know it's possible. OK, so I'm just going to change the notation a little bit now. Okay, so people often write, I mean, this is kind of the right way to write it, using variable equals value. But people often abbreviate to this. Again, this is probabilists making their own lives convenient, even though it's less clear. So this is probability of E given R and S. And you're supposed to understand from context that this means the probability that E will follow RS. And in order to eliminate that bit of notation at the top, let's use this beginning of sentence symbol. So I mentioned end of sentence before. Here we have beginning of sentence. So asking whether, now these all look like trigram probabilities. We imagine that we've started out with a whole row of beginning of sentence symbols. And then what's the probability that the next symbol will be H? And that once we've got H at the beginning of a sentence, that the next thing will be O. And at this point, we've now forgotten for the rest of these that we're at the beginning of the sentence. So everybody has a little bit of left context, 2 characters. And the first couple of characters, when they look at the 2 characters of context to the left of them, they're in kind of, they're in this ocean of beginning of sentenceness, the no man's land before the sentence starts. OK, I'm going to change the notation one more time. So this is making the same assumptions about language as these trigram dice do. And by putting these together, by multiplying these together, we estimate, we estimate the true probability of horses. We define this function P, which is a particular estimate. This particular function P is a probability model that we're using, and we hope it's close to the truth. Of course, is English really a trigram model? No, it is not. Okay, so this P is just an estimate. But it may be sufficient for the task of language identification. OK, so these are our parameters. These are the values of the parameters. And I said I was going to change the notation one more time. I just want to emphasize here, these are just numbers here, right? We don't have to call them probabilities at all at this point. So we're defining P of a string, P of horses, as being a product of these numbers. I think I picked T here to stand for trigram or maybe for table, because you'd look these up in a hash table, for example, or an array. So if you want to know what the probability is of E given R and S associated with this trigram, you would look that up. And here's the number that you would get. And how do you get it? Well, you get it by, I mean, where did that number come from? It came from counting things up in the Brown corpus. So here's our trigram model. Given a particular set of values of the parameters, we get a definition of P. And what can we do with our definition of P? One thing is we can roll our dice. So we can say, let's generate text according to this model. That's actually a good thing to do when you build a model. We'll do it this afternoon. when you build a model of language, you should see what that looks like. And then, in this case, we saw that with a trigram model, it started to be pronounceable. And with a 4-gram model, it started to have words. And with a 17-gram model, what would it have done? It would have probably just produced Genesis, right? Because for that particular set of 16 characters, that probably only appeared one time in Genesis. And there's only one character that could follow it. So it would just reproduce what happened in Genesis at that point. That model has no bias at all. It's exactly reproducing Genesis, but it has a very high variance as a model of English because it always gives you, it's completely dependent on this corpus that you estimated it from. If you really wanted a 17-gram model, then you'd need an astronomical amount of text in order to be able to generate something that looked like English generally and not just like the sample that you estimated it from. So once you've got P, you can generate random text. And more important for our purposes, given an event like a sentence, you can find out what the probability is. And in language ID, we say we've got the same model. It's got the same structure. We just have different parameters. We've got our English trigram numbers and our Polish trigram numbers. What comes out from that is two different probability functions. And then given some data x, a sentence, we can compute P of x and Q of x and decide which one is higher. So far, so good? OK. So I want to spend a few minutes now just talking about notation, making it a little bit more precise because people sometimes get confused about this. So this x here is an element of some event space. For example, the space of all races or the space of all sentences. If the event's a whole text, so we want to know the probability of a corpus, well, that's the probability of all those sentences together. And if we want that, it's pretty reasonable to take the chain rule and then back off. So if we want the probability of the whole text, we say let's pretend all the sentences are independent and multiply the probabilities of the individual sentences together. So just another example of what I've been repeatedly spewing at you. Is this assumption actually appropriate? Is it the case that sentence 2 really is independent of sentence 1? Probably not, right? If I talk about bread in sentence 1, maybe I'll talk about bread or butter in sentence 2, right? These things are related. Sentence 2 is unlikely to have a he or a she in it unless I've mentioned a person of the appropriate gender in sentence 1 or elsewhere in sentence 2. But this is not a terrible assumption. It's commonly made. All right, so I've said that x is an element of some event space. So if an event is a sequence of letters, well, that's kind of funny because this doesn't look like an element of an event space, right? This looks like a conjunction of different sets of events. This is the set of all sentences whose fifth letter is E. Okay, so we're taking an intersection of sentences whose first letter is H with those whose second letter is O, with those whose third letter is R. When we take this intersection, we get all sentences whose first 6 letters spell horses. Okay. So what does this notation really mean? I kind of hinted at it before. So x2 is supposed to be the second letter in the sequence. And I'm going to stick to my story here, that your event space is something like the set of all sentences. Every sentence is an event. x2 is the second letter. Here's another example. Our event is a sequence of 3 coin flips. But you might write something like the probability that the number of heads is 2, or you might abbreviate it in one of these ways. So what do we mean by that? Over here, the event is a race, but again, we were writing predicates, okay, which pick out some subset of the set of races. So what's going on here? The answer is that variable is really a function of the event, as I hinted before. So really, the right way of writing this is like this. Event is a sequence of letters. Any event is a sequence. x2 of event is the second element of the sequence. We traditionally suppress this part of the notation. When we ask if probability of h is 2, what we mean is the probability that we have some event whose h is 2. Okay? You can think of h as like a method call on the event, which tells you back some property of the event. In this case, how many heads were in that event. And similarly, races might be amazingly complicated events. They might talk about, if you know the race, you might be able to inspect the race and find out who the jockey was and what the phase of the moon was and whether the track was muddy and so forth. In this case, we're just looking at one property of the race, namely whether the weather's clear. Okay. So that's true of some events. It's false of others. One nice thing about the notation is that here we've said that the events are races, but we could get more complicated and say that the event was some even more complicated state of the world, and we could still pick facts out of it. Ask whether what the value of this function on the state of the world. So we don't really have to commit usually to what the event space was. We only have to commit when we're working out our models what things we have to be able to compute of the events. OK, so just to do this for a couple of the examples we've looked at, when we ask probability that the number of heads is 2, what we mean is the total probability of all events that have 2 heads. So that's the total probability of this set. Now we can divide this set up into 3 pieces, right? Because these are disjoint subsets. So the probability of heads, heads, tails, heads, and tails, heads, heads. And the total probability of those things is 3/8 if it's a fair coin. Yeah. Right. If it's a fair coin, actually we want to say 2 things. One is that the coin has a 50% probability of coming up heads, came up tails. The other is that the 3 flips are independent of each other, right? That it has no memory. Right? In that case, because it could be that that you could have a magic coin that comes up tails, tails, tails half the time, and heads, heads, heads half the time. Then it's half heads and half tails, right? But it's not the case that then 2 heads would have probability 0, right? Not probability 3/8. So we're making some assumptions here. For most coins, the assumption is correct. OK, so it's just another example. I guess I don't have to beat it over the head. And in our horses example, when we ask about the probability that the second letter is O, we're asking about the total probability of all events, all sentences whose second letter is O. So there's an infinite number of those, actually. But as you know, you can have an infinite sum an infinite summation whose sum is finite, right? Like 1/2 plus 1/4 plus 1/8. As these sentences get longer, what happens to their probabilities? Well, you're multiplying more dice together, right? The probability of the die coming up in a particular way is less than or equal to 1. So the probabilities will tend to go down as these things get longer. So it is like a geometric sequence. 1/2 plus 1/4 plus 1/8, and you do end up summing over all strings to 1. When you sum over all strings whose second letter is O, you'll get something less than 1. And that is going to be the probability that the second letter is O. So that's all it means. OK, so let's go back to this trigram model here. I want to suggest that we have a couple alternatives. Here's a different model. So what I'm trying to do by emphasizing chain rule and back off over and over is to say, look, you've got different choices here when you build a model about how you divide up the world, what you pick your variables to be, how you decide to order things in the chain rule, how you factor things, and what conditional independence assumptions you try to make. So I want to point out something that's kind of wrong about this model. It doesn't have a dictionary. So horses is a common word, right? And the model somehow is missing that horses is a common word. Horses is more common than the trigram method would predict, because the trigram method predicts all kinds of words that are not in the dictionary and which are really rare. It's when the trigram model does that, it's stealing probability mass that should rightfully belong to horses. I mean, I don't know why we picked horses and not schmorses. Right? Schmorses is a perfectly good English, well, let's say courses. No, horses is a word. Torses. We could have picked torses instead of horses. A trigram model would like that just as well, maybe even more. But English happens to have picked horses, and our model doesn't know that. Our model only knows that HOR and ORS and RSE and so forth are likely. Okay, so how could we learn from the corpus that horses is a common word? Well, one thing we could do is instead of talking about random variables like x1, the first letter, we could talk about random variables like w1, the first word. So we can divide, as long as we have some function which, given the sequence, is able to split a sequence of characters, is able to split it at white space, we can compute w1 given an event. Right? So we can talk about the probability that w1 is horses, and if we run our white space splitter on the Brown corpus, then we can find the number of sentences whose first word is horses. Okay. That's this. Let's back off. So we'll back off to just how frequent is horses in the corpus. And we get 7.2 times 10 to the minus 5. Now that actually is a lot higher, I think, than what we got previously. Where's our number previously? There we go. So it was 5.4 times 10 to the minus 7. And here we have more than 100 times more likely than the trigram model thought. Okay? So this is just really a signal that the trigram model is getting something wrong. The trigram model thinks that horses ought to be more than 100 times less frequent than it actually was in the Brown corpus. And that's because it just doesn't know that English happened to have picked the word horses rather than torses. It gives them both about equally high probability, and that turns out to be wrong. Okay, so one advantage to using a model based on words is that it gets the probability of this more right. It knows what the dictionary is. A disadvantage is what happens if a word shows up, like Łukasiewicz, which is not in the Brown corpus. Well, the trigram model would still give it some probability because all those sequences of 3 letters are still probably in the Brown corpus somewhere. But that word, that Polish name, is nowhere in the Brown corpus. And so the Brown corpus would estimate probability 0 without backing off. Okay, so the advantage is that we focus more probability mass on stuff that we've actually seen. In some ways, this is like a 6-gram model or something, right? Because it's looking at longer sequences to know whether the thing is likely. But it has the same disadvantage that any of these higher order models have, like 6-gram or 17-gram models, which is that it's putting a lot of net probability on things that it's seen and leaves none behind for things that it hasn't seen yet but might someday. So the advantage is focus is better on what it's seen. Disadvantage is the flip side of that, which is maybe it's overfitting to the training data. It's focusing too much on what it's seen. Okay, so let's improve them. Let's stick with this, but let's improve the model a little bit. So we've made this independence assumption back here that whether word I is horses is independent of what I is. So is that actually true? I'm going to argue it's not quite true. Okay, I as one is not irrelevant because the first word of a sentence is usually a determiner, a word like or the or every. Okay? Not always. Horses could show up at the beginning of a sentence. But it's just that horses is probably a plural noun, and we're less likely to start a sentence with a plural noun. So maybe we should care that I equals 1. So I'm going to suggest that we do this split, right? There are a lot of ways for the first word to be horses. One is that the first word could be horses, and the tag, or part of speech tag of that word, is noun. Another possibility is the part of speech tag is verb. Another possibility is that it's determiner. So remember that if there's some event that we want to estimate, we can split it up. We can split up that set into disjoint subsets. So lots of disjoint subsets here, summing over all possible part-of-speech tags. So we're bringing that variable into our model. Well, once we do that, we can now factor by the chain rule. Probability that word 1 is horses, given that the first tag is t, times the probability that the first tag is t. And now what I'm going to suggest is that we back off over here. Okay, so we're going to say that the first piece doesn't care whether I is 1. So that's why we have this approximation here. It's because we decided to ignore that. So what this is saying is, what's the, actually, let me expand this. So this is saying, what's the probability that the first tag is a plural noun times the probability that if you had a plural noun anywhere, it would be horses. I backed off here because we probably don't have enough data in the Brown corpus to figure out whether a plural noun at the beginning tends to be horses. But we can ask whether a plural noun tends to show up at the beginning, and then if a plural noun shows up anywhere, whether it's horses. If you were going to get a plural noun at all, would it be horses? So this is a kind of a reasonable model. And here are our two factors. So we have 56,000 plural nouns, of which 72 are horses. We have 52,000 sentences, of which fewer than 1,000 start with plural nouns. And now instead of 7.4 times 10 to the minus 5, we only get a third of that. So our probability has now gone down by a factor of 3, much as we expected, once we take the parts of speech into account. Okay. So this is a more refined model, because it's not completely forgetting about I equals 1. It's not just asking how often does horses tend to appear in the corpus. It's asking how often does horses tend to appear in contexts like plural noun that tend to be at the beginning. Now, I did drop this summation here. This estimate might be a little low. We should also say, OK, how often is the first thing a verb? And when you have a verb, how often is that verb horses? Horses can be a verb, right? You know, like my son horses around a lot. It's just very unlikely, so I only included this sum in. But to be proper about this, we should really add T1 as verb times probability of horses given verb plus T1 equals determiner times probability that horses, if you have a determiner, it's horses, which I hope is 0. But this is pretty close to what we'd get if we did that. OK, so which of these models is better? Here are the two models we looked at. This trigram model. And this other model, which predicts every word by its part of speech, having predicted the part of speech from the position in the sentence. How would we decide? They're making different independence assumptions, right? So how would we decide which one actually works better? Well, let's try it on some data. One thing is we could evaluate on a particular task, like language identification. So we've got some test where we know the correct answers. I'm going to be done, by the way, in about 2 minutes, I think. I'm afraid I'm running into the break a bit. So we're going to administer a test where we know the correct answers. We seal up. We train on some examples of English. We train both models of English and both models of Polish on some training corpus of English and some training corpus of Polish. And then we have a bunch of documents which are in either English or Polish, and we know which. But these didn't appear in our training data, so the model couldn't have memorized them. And so that's what I mean by sealing up the test data until the test happens. And we want to be fair about this, right? Because when you use this for language ID in the real world, the model won't have had the advantage of having looked at the real world examples in its training data. So we seal up the test data, so it's just like real world data. And we want to make sure that we have enough test data that we're sure that one kind of model beats the other kind of model well. So that's all we do. We say, OK, this thing got the right language 90% of the time, and that one got the right language 95% of the time. Actually, for any reasonable model, reasonable training corpora, you should expect on this task to get 99% accuracy easily if your input documents are not tiny. So if you had a different task, you could use that to evaluate the models. There's another way, which is task independent, that I want to mention, because it'll be important this afternoon, and then I'll close. So if you want to know whether the model is a good model, remember what happened when we tried to predict horses with a trigram model. In some sense, it didn't do a good job, right? Because it made it about 100 times less likely than it actually was in the Brown corpus. So it was not very good at predicting even its training data. When we measure cross entropy, we ask, OK, if this is such a good model, it should be able to predict the future, right? So let's take some future, some data that the model's never seen, and ask whether the model assigns high probability to it. Okay. In other words, how surprised was the model? One nice thing about this is that this is just asking whether the model is good at predicting data, not at whether it's good at a particular task. So if you're going to use a model for several tasks, this gives you some independent way of assessing its quality. Another reason it's nice is that if you don't have too much data to evaluate on, then you're often in a situation where you've got one model, you make a little change to it, to the way you estimate or something like that, and you used to be getting 503 answers right. Now you're still getting 503 answers right. Okay, so there appeared to be no change. But cross entropy, as we'll see, will notice whether the things that you're getting right, you're getting more right now or less right. In other words, are you giving a higher probability to the surprise test examples than you were before, even if it wasn't enough to make a change in whether you predicted English versus Polish. Maybe you're even more confident that you had English than you were before. OK, so the way you do this is you just take some test data and you measure its probability. If you have a higher probability, that means the model was better at predicting the future. And you'll never be able to predict the future with 100%, right? You'll never be able to assign probability 1 to data in the future. But you can maybe do better with one model than another, and that's some indication that that model is doing a better job of capturing the generalizations from the training data in a way that projects forward into the future where you look at test data. OK, so this is the last slide. So we want the probability of the test data to be high if the model's good. So this is the probability of the test data under the trigram model. Looks like that. So cross entropy is related to probability in a simple way. We're just going to make a few improvements so that these numbers are easier to work with. The first improvement is that to avoid having to deal with this very, very small number, the probability of this sentence, instead of multiplying these numbers, that will add their logarithms, which amounts to the same thing. So the log of this product is the sum of the logs, as I'm sure you know, which is, so -3 is the log of 1/8, -3, -3, and -4 is the log of 1/16. So that's the first thing. Then, since all these are negative numbers, because there are logs of things that are less than 1, logs of probabilities, we may as well drop the minus sign for convenience. And this gives us a positive value. And the unit here is bits. So the reason is, if you had 8 equally likely things, each of which had probability 1/8, and you wanted to communicate which of those 8 things you had, which of 8 letters you had, for example, you would need 3 bits to do it. If you had 16 equally likely things, each with probability 1/16, then it would take 4 bits to communicate. So this is, I won't go through the connection, but this is closely related to how you do optimal compression of text. The better a model you have, the better a predictive model you have, the better compression you can do. And the cross entropy tells you how well your model would compress the test data, how many bits it would compress to. So the third improvement is that this is the total number of bits. If we want to know how good the model is, we don't want to have to worry about how long the test data was. So we'll divide by the length of the test data to get bits per letter. Or if you were doing a word trigram model, maybe bits per word. And we want this to be small. So again, that's saying we'd like to be able to compress into few bits. So in this case, this is 3.25 bits overall. And there is some lower limit on this, which has to do with how random this type of data is. But the better a model it is, the closer we can get to that lower limit, which is called entropy. OK. There's another number that people sometimes use, which is 2 to the cross entropy. So we did a log base 2. We kind of undo that log by taking back to a power of 2. So instead of 3.25 bits, we take 2 to the 3.5, which is about 9.5. So here we have, you can think of that as the geometric mean of 8, 8, 8, and 16. In other words, 8 times 8 times 8 times 16, take the 4th root, because we had 4 things, is about 9.5. So these are things, these slides are online if you want to go back over any of this. At this point, I've used up half of your break. We are actually going to need, unfortunately, the full time, I think, from 10:45 to 12. So I guess it'll be a 15-minute break. I apologize for that. So we're going to do something pretty cool after the break, but I needed to put this foundation in place first.